Hey guys, today we're going to be looking at specifically dilution problems. We're going to look at the techniques involved in diluting solutions, and I'm going to show you how to represent dilutions on particle diagrams. First thing we need to be aware of is, what is a dilution? Well, a dilution is simply reducing the concentration of a solution by adding more of the solvent. In most of our situations, that's going to be water. So if we have an aqueous solution, adding more pure water will dilute the solute in the solution. The two techniques of dilution that we're going to talk about in terms of experimental techniques are going to be serial dilutions and stock dilutions. So today we're going to talk about both of those things. We're going to represent it also with a particle diagram. The biggest thing to remember is that in any dilution situation, the number of moles of your solute never changes. We're just adding pure solvent. So if we're just adding pure water, the number of moles of any solute we had in the original solution will never change. That's really handy to remember and keep in mind as we're going through this. So what does a dilution look like in a particle diagram? Well, check out this beaker. In this beaker, I have a certain number of molecules, or ions, or particles, and I'm going to simply add water to that beaker. And when I add water, as you can see, what happens is the number of molecules or particles didn't change, but there's now more volume. Remember, molarity is moles per liter. So we haven't changed the number of moles, but we've changed the number of liters. We've increased it. That means our total molarity has now decreased, all right, because we've increased the value of our denominator. First technique we're going to talk about in terms of making a dilution is going to be a serial dilution. Now, serial dilutions are functional for diluting an initial stock solution, and they're really helpful if you don't have a lot of stock solution to begin with. It's really a technique that is helpful, but there is some error-prone nature to it as well. So we're going to talk about the potential pratfalls of serial dilution as well. With a serial dilution, if you look at my technique diagram down below, what you see is we start with 1 milliliter of our stock dilution. Now, the stock dilution would be the solution we started with. We take 1 milliliter and we dilute it with 9 additional milliliters to get to 10 milliliters. This means that our overall concentration has been reduced from 1 to 1/10 of the original starting concentration. So the new second solution is 1/10 the concentration of the first. We don't have to have it as 1/10. It could be 1/2, depending on how much of the stock dilution you start with and how much you then put into the secondary container. Essentially, what we're going to do is we're going to repeat this process. So I'm going to take my initial stock dilution. I'm going to take 1 milliliter out of it. I'm going to put in the second container. I'm then going to add 9 milliliters of water to bring the total volume up to 10 milliliters. I'm then going to take 1 milliliter out of the second container that I just created, and I'm going to put it in the third container. I'm going to add its volume up to 10 milliliters by adding 9 milliliters of water. I'm going to repeat this process over and over again, and every time I repeat this process, in the example I'm giving you now, I reduce the concentration by 10 times. Like I said, you can do this with any value. I could take 1 milliliter out and add only 1 more milliliter. So I cut the volume, or I double the volume, which means I cut the concentration in half. You can do serial dilutions in any way, but the key here is that you're always taking from the most recently created solution. The challenge here is, what if I made a mistake? What if I made an error on the second container? Well, then that error is going to persist all the way through every other one that I create from then on out. So there's a challenge in serial dilutions where you have to be extremely careful when making every single one, because any mistake made in an early dilution is going to be seen in every dilution after the fact. All right, let's do a practice problem with a serial dilution. If I start with a solution of 0.25 molar, I need to know how many times to dilute it to get to 0.0025 molar, using a technique where I took 1 milliliter of my solution, added 9 additional milliliters of my solvent. How many times would I have to do that in order to get to my target concentration of 0.0025 molar? Well, if you look at it, the first time I would do this, I would take 1 milliliter out of my stock, dilute it to 10. That means my volume multiplied by 10, which means my concentration divided by 10. In order to do this to get to 0.0025, I have to do this twice. The first time would get me to 0.025, and then the second time to 0.0025. So serial dilution is fairly straightforward, but like I said, there's some risks in serial dilution if you make a mistake in the first or second dilution step. For example, if I were to ever make an error where I accidentally took fewer milliliters of my stock solution than I wanted to. I wanted to take 1 milliliter, but let's say I take 0.9 on accident. This is very possible because we are using instruments that might not be super precise. I mean, we're not trying to save lives here. So the idea here is that if I didn't quite grab enough of my stock solution, and then I still diluted up to 10 milliliters, I've actually created a solution of lower concentration than I would have predicted. From that moment on, every dilution I make using that next solution that I just created will also have a lower than predicted concentration. The same kind of error can happen if I accidentally took too much. If I accidentally took too much of my initial stock solution, or of any solution there on out, then I'd see a higher than predicted concentration in every single solution from that moment onward. In AP chemistry, we tend to use stock dilutions more often. The reason we use stock dilutions is because if one mistake is made at any point in time, it only impacts one measurement. It doesn't impact the rest. But the problem with stock dilutions is that you require a whole lot more of your original stock solution. If we ever have a solution that is, let's say, rare or exceptionally expensive, we'll often opt towards a serial dilution. But for most of ours in this course, we use stock dilutions because it mitigates a lot of that potential errors that can happen. Also for a stock dilution, we don't have to necessarily cut each concentration in half. We can do a lot more in terms of finding exact, precise concentrations. And the way we do this is just like we would do when we make any solution. If I want to make a 0.1 molar solution, I figure out how many moles of my solute I need, figure out what the total volume needs to be, and I simply add that number of moles of solute to create that solution. As with any solution, the best tool to use for this is a volumetric flask. In a volumetric flask, we're going to add the solid to the bottom of the flask. We're then going to fill slightly with water. We're going to shake it around a little bit to dissolve the solid. We're going to fill it all the way up to the line, the hash line on the volumetric flask that represents the precise volume indicated on the flask, be it 100 milliliters or 250 milliliters or 2 liters, whatever you might be using in this situation. Let's do an example problem for a stock dilution. If I have a stock solution of sodium chloride of 0.25 molar, I need to create 250 milliliters of a 0.1 molar solution. How am I going to do it? This is the situation where M1V1 equals M2V2 comes really handy. So M1V1 equals M2V2, where 1 represents our initial solution and 2 represents our final solution. So molarity of the first one, that's our stock solution. So that's 0.25 molar. Now, I need to get to a final solution of 250 milliliters, which is 0.25 liters, and 0.1 molar. So what I'm going to do is I'm going to plug in, and I realize that the only thing I'm missing is V1, the initial volume of my stock solution necessary to get to my final solution. What I'm going to do is I'm going to solve for V1. And what I realize is that I need 0.01 liters of sodium chloride solution, of this stock solution, to be able to create 250 milliliters of my final solution. But wait, I had just said I took 0.01 liters. So what I need to do is I need to take that 0.01 liters, I need to add it to a volumetric flask, and then I'm going to take the volume and I'm going to fill it all the way up to a 250 milliliter volumetric flasks line. That's going to give me exactly the volume and the concentration of the solution I need for this situation. I talked briefly about the errors that could be involved in stock dilutions. And overall, it's less prone to error than it is in a serial dilution. Not because of the fact that any one measurement error is less likely, but more so that any one measurement error only affects that one solution. If we have a situation with stock dilutions where you accidentally measure too little of your solute, your concentration is going to be too low. If you accidentally measure too much of your solute, the concentration is going to be too high. So let's go ahead and do an example problem with stock dilution. Again, we're going to use the M1V1 equation where M1V1 is equal to M2V2, knowing that The M, capital M, is molarity, moles per liter, and V is going to be volume. Now, if you do the math, what you'll realize is that we're simply saying moles is equal to moles. Moles initial is equal to moles final. And that's critical because any dilution is going to keep the number of moles present the same. The only thing we're changing here essentially is the volume, which impacts the concentration. So let's do an example problem. If I've got a 0.1 liter solution of 0.25 molar sodium hydroxide, I want to figure out, by adding 0.1 liters of water, what would the final concentration be? In order to do this, I'm given the initial volume and the initial molarity, and I'm given the final volume. But be careful. I'm given the final volume, but it's actually not a number that you see here. In order to get the final volume, I have to realize that I've taken an initial volume and I've added volume to it. So I have to add the two volumes together to get my final volume. This means our setup M1V1 equals M2V2 would be 0.1 times 0.25 is equal to, in this case, M2, which we don't know yet, times 0.2, because we've simply doubled the volume here by adding the two together. That gives us a final answer of 0.125 moles per liter. So my new solution would be at a concentration of 0.125 moles per liter. All right, that wraps up today's video. We learned today a couple of techniques of diluting solutions from a stock solution to a targeted concentration. The two techniques we looked at were stock dilution and serial dilution. Again, we're going to see a lot more stock dilution this year in chemistry, but you need to be aware of both techniques. You also need to be aware of the potential ramifications of errors in both techniques, because that's a very common problem or test type problem that comes up often. I'd like to thank Emma Dizdari and Jen Worth for writing, filming, and editing this video. I'd like to thank you guys for watching it. I'll see you in the next one.